Hello, I'm Manashwa Chatterjee. I'm an assistant professor at the University of Copenhagen, and I'm going to tell you today about experimentally how we would like to auto-tune a quantum computer. As we all know from previous videos and also our own experience, we all use logical bits. In fact, many of them, billions of them in our everyday lives. They form these chips that sit in your mobile phones and your laptops, and they're essentially made of large arrays of transistors, which are going 0, 1, 0, 1. They're switching between 0 and 1s, encoding physical bits of information in a digital way, and that's how you do most of your computation. That's how this video is brought to you today. If you now want to implement something called a quantum bit, you want to implement something that has a larger, we can say, a Hilbert space, where, for example, you could imagine implementing it in a spin of an electron. And here, the spin of the electron could be in a state 0 or a state 1, or in some superposition of these states, which you can see in terms of a Bloch sphere, which has can have the electron spin pointing at any point on a surface. But how do we actually make such arrays of qubits? So if you think of this qubit as an electron that is trapped by a voltage, which is applied to gate electrodes, then you see that in order to make anywhere near the number of transistors you have in your phone, you need to make these 2D arrays with two or more of these gate electrodes, which can switch the qubit to 0 or 1 or some other state. And you need to repeat this process in, on the scale of thousands, at least to billions. And so this is a very resource intensive process, and you really don't want to do it by hand as it is done in laboratories today. First, a little bit about electron spin qubits. They are usually, at least the ones that I and some others work on, are hosted in something called the quantum dot. It's a region of space where these gate electrodes form a sort of metal cage using voltages to trap an electron in there. It was proposed quite some time ago as a kind of canonical qubit. And since the electron has spin and which can be manipulated in different ways, and they can have very high coherence times, which is why we like them. And the first transistor, which was actually made in germanium, is an example of a material which is now used to make qubits. So there are germanium whole qubits, for example, or there are transistors that are now made in the foundries, which have now been shown that the electrons trapped in these transistors can be used as qubits as well. And the type of qubits that I will talk about today are those that are implemented in heterostructures. And these are kind of, if you look at the cross section in the picture, they're essentially a sandwich of materials, very cleverly designed, such that in the middle there is a sheet of what is called a channel, where there is a sheet of either electrons or holes that are trapped, forming a kind of C, a two-dimensional C that you can shape. And how do you shape them? Well, one of the things you can do is make gates on top, which you can see via this top view picture. And I just say a little more about that. For more information on heterostructures, you can watch the course video made by Giordano Scapucci. For a two-dimensional electron gas, one thing you can do is you can take your little nice material sandwich and put electrostatic gates on top. These are usually metal, and you can apply a voltage to these gates, for example, negative, to repel electrons, which are also charged negatively. And if you now apply such a negative voltage, you will see that from the top view, there will be a region of space where there are no electrons, for example, here. And now, if you dial back these voltages just a little bit, the voltages in the middle, then it will be favorable for just one electron, for example, to hop into this puddle, forming your quantum dot. And you can do it to form two next to one another, and so on. And now, if you apply an external magnetic field denoted by a B, then whether or not your electron spin is aligned or anti-aligned, you can have a qubit by defining your qubit. So that's how we would tune and make these qubit processors. However, one of the problems we want to solve is how to do the tuning and operation of arrays that are larger than just trapping, a single or two electrons. And the tuning of operation of arrays becomes quite difficult when you start to look at a 4-qubit device, which was made at the University of Copenhagen, which already has 48 gate voltages. And here, this would mean that you would have to, by trial and error, find 48 voltages that you have to apply on each of these electrodes. And this can take quite a while, especially because your voltages can drift and move around over time. So it would be much better to have, for example, a computer do this instead of a graduate student. And one of the things that you can see is that other arrays, including ours, are getting very, very complex. Here are some devices. One is from Princeton, one is from Delft, and the other one is from HRL Laboratories in the US. These are linear arrays, but you can already see that they're quite complex. If you look at 2D arrays, they also are getting very complex. There's a device from Delft and a device from Grenoble here, which encode 2x2 and 3x2, 3x3 arrays. And if you look at a recent array from, again, from Delft, there is a 4x4 array of quantum dots, and this is, again, quite a complex device. So I hope it is clear that it really needs efficient and fast algorithms to tune such quantum devices automatically.